So started, right? Okay, so 1 minute. I think I have to. 1 minute. So my audio is on. Video. Okay, 1 minute. Stop presenting on video. Yeah. Now start presenting. Okay. So I will start present now, right? Okay. So okay, students. So am I audible to all of you? Yeah. Good evening. So it's fine. So am I audible? So you can answer in chat, students. And my PPT is visible to you? Okay, okay. Okay, so date is different because it was made that day. So, okay. So today I will be starting this reanalysis unit 2 part, that is reanalysis and matrix algebra, and the part I have assigned is part 3, that is matrix algebra. So, as you know about me, my name is Dr. Santosh Kumar Chaudhary. I'm currently assistant professor in Department of Statistics, Central University of Jharkhand, Ranchi. So we will be discussing these 3 sessions. The session 1 has contents, vector spaces, subspaces, span, linear independence, basis, dimension, row space, column space, rank and nullity, then row reduced echelon form, trace and determinant, inverse, and system of linear equations. Then session 2 will discuss Smith orthogonalization, characteristic roots, and characteristic vectors. Then characteristic polynomial, Cayley-Hamilton theorem, and the session 3 is symmetry matrices, two symmetric matrices, orthogonal matrices, and their characteristic roots, positive definite and positive semi-definite matrices and quadratic forms. So these are linear algebra part that you might have done in UG and PG level. So like in session 3, matrices you already have done at school level, Cayley-Hamilton theorem, all that. That was in school level also, matrix and determinant chapter. So let's start with the session 1 contents. And so question is, what is a vector space? So how to define a vector space? So the screen you can see, this is a definition of a vector space. So a vector space actually is a set V over a field F. So field is set of scalars. So a set from which scalar will come from, like F may be set of real numbers, set of complex numbers. So it's a set of scalars. Scalar is constant. So set of constants actually. This F is set of constants, and V is a vector space. So elements of V will be called vectors, and elements of set F will be called scalars. So a vector space V over a field F is a set with 2 operations. So vector space is a set V with 2 operations, and addition and scalar multiplication. These 2 are operations with a set over a field F. So field F is important because that scalar you will choose from which set. So that set is actually filled. So vector space V with a field F and 2 operation, addition, scalar multiplication. So addition means whenever you choose, this is called closure property under addition. So when you choose any 2 vectors from, so vectors are actually elements of vector space or set V here. So you choose any 2 element from set V, then their sum must be in set V. So this we say it is closed under addition. Set V is closed under addition. And then scalar multiplication is what? So you choose any alpha from field F and V from a set V. Small v is a vector and capital V is a vector space, or you can just set small v is an element. So small v belongs to capital V. So for any alpha in F and for any V in V, alpha into V must be in the set capital V. So this property is called closed under scalar multiplication. And then V to be vector space, it has to satisfy these 8 axioms. So that 8 axioms must be satisfied for V to be a vector space. So what are the axioms? The first is U plus V plus W should be equal to U plus V plus W. So here you can see the differences in brackets. So this is called associative property. So operation addition must be associative. Then U plus V should be V plus U, that is called commutative property. And then the third one is there exists a zero element. So that zero element actually additive identity. So there exists an additive identity such that V plus 0. So here 0 represents identity actually, additive identity. So V plus 0 should be V. Then every element should have additive inverse. So for every V in capital V, there exists a minus V in capital V such that V plus minus V should be 0. So this is called existence of additive inverse. And next fifth is just it is associative over scalar multiplication, you can say. So alpha into beta V should be equal to alpha into beta times V. So the difference of brackets. Then 1 into V. So 1 is the multiplicative identity here. 1 comes from set F, it's a scalar. So 1 into V should be V. And then alpha into U plus V should be equal to alpha U plus alpha V. Alpha plus beta into V is equal to alpha V plus beta V. So here alpha and beta are scalars and V vectors. So alpha beta come from field F and U, V, W that we have used come from V. So V is a vector space over F with two operation addition and multiplication said to be vector space if they satisfy these axioms, and these two conditions are closure property that must satisfy. So in all you can say there are 10 conditions. A set with a field and with two operation is said to be a vector space if they satisfy these 10 conditions. This is also a condition. For any two element in V, the sum must be in set V, and then for any alpha in F and V in V, alpha into V should be in V. So this is a definition of vector space. So you may check whether set of V, we can check set of real number, F also set of real number. So you can check set of real number is a vector space over F or over R. Just they will satisfy all these conditions, and few of you might be thinking they are trivial conditions, but they are trivial in case of few examples, but they are non-trivial in case of many examples. Okay, I think so. If you have any doubt, you may write in chat, so we'll see there. Okay. So next, this was just definition, so it's repeating. For example, so the repeating, first thing is repeating last definition. So what are some examples? So like for example, capital V, you can take Rn. Rn is a set of n tuples where each tuple will come, each element in the tuple will come from R. So it's a set of all n tuples of real number. So this is a vector space over R. M cross n R. This is set of all M cross n real matrices. So here the addition will be matrix addition and scalar multiplication will be scalar multiplying to matrix. Then these are vector spaces. These are few trivial examples, easy examples. The set of all polynomials of degree less than equal to n. So this is also a vector space. Now their terms subspace. So it's like set and subset. So you can similarly connect space, vector space and then subspace. So the definition of subspace is a non-empty subset W of V is subspace if it is itself a vector space under the same operations. So this is a definition of subspace actually. Only this one. So a set W which is subset of V this is called a subspace if it is itself a vector space under same operation. So operations would be common. And then there is a theorem. So this is subspace test. This is a theorem actually. So subspace test means like they are saying, if you have a subset W of V and you want to check whether W is a subspace or not. So to check whether W is a subspace or not, you have to check these three conditions. So like 0 must belong to, 0 element must be in W, and that 0 element will be common in V and W actually. So 0 element must be in W. You choose any two element in set W, their sum must belong to the W itself. For every UV belongs to W. So, and then you choose any alpha from F and any V from W, then alpha into V must be in W. So these are three conditions you can check to make sure that set subset W is a subspace. So in examination, this is actually important part, because usually mostly you will find one question based on this. So you will have four options and they will ask you to check whether which of the following is a subspace or not. So they are most frequently asked in all entrance examinations wherever vector space is part of the syllabus. So this you should remember and practice few questions based on that, because this is an important point and they will ask. So you have to just check this. They don't ask to check the vector space. Like this definition is just for information. They don't ask whether there is a vector space or not. In fact, you just check a subspace condition, and if this happens, then it will be a vector space actually. So you have to check these three conditions only to make it a subspace. If it is a subspace, it is also a vector space, because subspace is a subset which is a vector space. Okay, and then for example, so set of all symmetric matrices. So earlier we have taken M n cross n. This is the M n cross n is a vector space of set of all n cross n matrices, and this is a subset. So set of all symmetric matrices is a subset of M n cross n. So this will be a subspace of this. M and n is V actually, and W is set of all symmetric matrices. Then again, V was Rn. So when you take capital V is Rn. So W you can consider solution set of homogeneous linear system Ax is equal to 0. This is also called null space of A. Later we'll define. This is the null space of set A. Matrix A. So null space of matrix A is a set of all x such that Ax is 0. So this null space will be a subspace of Rn. So then there is a term called span. So span, what is a span? So given vectors v1, v2, vk, so the span is defined as, so their span of vector v1, v2, vk is defined as set of all linear combinations. So this is called linear combination. Alpha 1 v1 plus alpha 2 v2 and so on, alpha k vk. So this is a linear combination, and where alpha I belongs to f. Okay. So this is set of all linear combination of v1, v2, vk. So a span of v1, v2, vk is actually set of all linear combinations, where alpha I belongs to field f. So mostly field we consider set of real number or set of complex number. So mostly it is when you say vector space over R, so means f is R actually. When you say vector space over C, so then f is C actually. So it is the smallest subspace containing those vectors. So span of this v1, v2, vk, this will also form a subspace, and this will be the smallest subspace containing all those vectors. So you take any other subspace containing these vectors, that will be larger than the span. Then the term is linear independence. So how to define linear independence? So vector v1, v2, vk are said to be linearly independent vectors. So v1, v2, vk, they are all part of vector space, elements of vector space. So they are said to be, these vectors said to be linearly independent if and only if. So all definitions are if and only if. Even it is just if, but it is if and only if. So vectors are linearly independent if and only if alpha 1 v1 plus alpha 2 v2 and so on, alpha k vk is 0. Implies alpha 1 is equal to alpha 2 is equal to alpha 3 and up to alpha k is 0. Means when you put linear combination equal to 0, all alpha i's has to be 0. There is no alpha i's that will be non-zero. If any one alpha is comes to be non-zero, or there is a possibility of being non-zero, then it will be dependent vectors, like here. Otherwise, they are linearly dependent vectors. So you put linear combination equal to 0, solve this equation, and you will see that all constants has to be 0. All alpha i's has to be 0. If at least one or any one becomes non-zero in any situation, then this has to be dependent. That's the definition. I will also show a few questions. So examples in R square. So just for example, like R square is a vector space. So V1 is 1, 0, V2 is 0, 1. Now you can check these two are linearly independent. So when you put C1 time V1 plus C2 time V2 and put it 0, simplify this equation, you will have two equations and two unknowns, and you will see C1, C2 will become 0, or alpha and alpha 2 will become 0. And the other example, if you take V1 as 1, 2, V2 as 2, 4. So they are dependent vector. You can simply see they are multiple. So multiple vectors are actually dependent always. So 1, 2 को अगर 2 से multiply करोगे, so you will have 2, 4. So they are actually dependent vectors. Or you just go through definition. So like alpha 1 V1 plus alpha 2 V2 is equal to 0. So you will realize there are many non-zero scalars available that will make linear combination 0. For example, you take -2 time this V1 vector and plus 1 time this V2 vector, then it will make it 0. So alpha 1 I have taken -2 and alpha 2 I have taken 1, and that linear combination is 0. So we have non-zero possibilities of scalars that makes linear combination 0, and that's why they are dependent. Then there is a term basis. So what is the definition of basis of a vector space? So a set of vectors. So this capital B is a set containing vectors B1, B2, Bn is said to be basis of a vector space V. So this set is said to be basis of a vector space V if and only if the first condition is that set B must span V. Means span V matlab every element of vector V can be written as a linear combination of elements of set B. So you can generate all elements of vector space through vectors B1, B2, Bn. So this is the first condition is, so B spans V. So you can also say a span of B is equal to V, that you can say. And the second condition is B set must be linearly independent. So a set of vector is said to be basis if the first condition is span of that vector should be equal to vector space, and second condition is that vector must be linearly independent, or vectors of that element must be linearly independent vectors, or that set must be linearly independent. Okay. So span B is equal to V means every element of vector space can be written as a linear combination of elements of set B. Then what is dimension? So dimension is just the number of vectors in any basis of V. So like number of element in the basis. So basis is not unique. A vector space may have infinite number of bases, but the one thing common is all bases must have equal number of elements. So all bases will have equal number of elements. So number of element in the basis is unique, but basis may not be unique. For example, like here was example. So you take vector space as R square. V1 vector is 1, 0, V2 vector is 0, 1. They are independent, and you can check they span the vector space. So these V1, V2 will form a basis of this vector space. And other than this, you may have infinitely many bases. Okay, so dimension is just number of element in the vector space. Okay. So here is one example. So like a vector space is taken Rn, and E1 is a vector 1, 0, 0, E2 the one in the second position, En one in the nth position. So you have taken n vectors, and they are linearly independent, and span of these vectors will be equal to Rn. So we claim that they form a basis. and dimension of this dimension of this. So actually dimension is a vector space. Okay, so dimension of a vector space is equal to number of element in the basis of a vector space. And you know, basis is not unique, but elements in the basis must be unique. Whatever basis you take, number of element will be common in that. So here we have E1, E2, En as vectors. They are linearly independent, and they also span the vector space, and that's why they will form basis, and the dimension will be n of that vector space. The second example is vector space. You consider 2 cross 2 symmetric matrices. So this is a vector space. Then you consider vectors as v1 1 0 0 0, v2 0 1 0 0, v3 0 0 0 1. So now it is set of symmetric matrices now. So these three are linearly independent vectors. How will you prove? You take C1 V1 plus C2 V2 plus C3 V3, put it equal to 0. Then solve that equation. You will get C1 is equal to C2 is equal to C3 is equal to 0. So they are linearly independent. And then you take a span of this. So it will generate all elements of this vector space, symmetric 2 cross 2 matrices. So these vectors are linearly independent as well as spanning set. And that's why these three vectors will form a basis. And that's why the dimension of that vector space will be 3. So everything clear till now? So, okay. So basis dimension we have done. So what was in session 1? It was still system of linear equation. Okay, so first I will discuss it, then we'll discuss a few questions. So we have discussed till here. Okay. So now next term is what is a row space, what is a column space, what is the rank of a matrix, and then what is the nullity or null space. So nullity is a number, dimension of null space. Null space is a vector space, and nullity is a dimension of that vector space actually. Okay. So for a matrix capital A, which is M cross N matrix over a field F. So you may consider F as set of real number. So you can say A is a M cross N real matrix. So what is a row space? So it's a span of the row vectors, or you can say span of row vectors. So suppose it has M number of rows. So you can take first row as V1, second row as V2, third row as V3, and the mth row as Vm. So V1, V2, Vm are vectors. So you take a span of that. So a span of row vector, or you can say set of linear combination of row vectors. A vector space generated by row vectors is called row space, or you can say span of row vector. So you have already seen span of vectors are vector subspace or vector space. So the vector subspace generated by row vector or span of row vector, these are called. So this space will be called row space. And similarly for the column space, vector subspace generated by columns of a matrix. So you take first column as U1, second column as U2, third column as U3, and there are n columns. So nth column is Un. So U1, U2, Un, you have n number of column vectors. And then, so the vector subspace generated by these column vector, or you say span of these column vectors, is called column space. The column space, row space, these are vector subspace. Then what is a rank? So if you take dimension of row space, so dimension of row space means the number of element in the basis of row space. And if you take dimension of column space, so it will remain same. So row space and column space, they are two different vector spaces, but they will always have equal dimension. And that dimension is called rank of the matrix. So whether you find a number of linearly independent rows or you find number of linearly independent columns, both will be always equal in any matrix. Even it is 10 cross 20 matrix. Still the number of linearly independent rows and number of linearly independent column will be equal. And that is equal to the rank of the matrix. So what is a rank? So rank of a matrix is dimension of row space is equal to dimension of column space. So dimension of column space means number of linearly independent columns of a matrix. Dimension of row space means number of linearly independent rows of a matrix, and they will always be equal, and that will be equal to rank of the matrix. So rank one way is to find number of linearly independent rows, other way is find number of linearly independent column, and that will be same. So, or you may find row space first, then find the dimension, column space first, you find the dimension, that's all. What is a nullity? So nullity is a dimension of null space. And what is a null space? So this is a definition of a null space. You can see. So null space is this one. So null space is a set of X such that AX is equal to 0. So set of solution vectors actually. Solution of what? Equation AX is equal to 0. So this is actually system of linear equation. So the set of all solution equation AX is equal to 0, that will be actually okay, so this is the null space, and dimension of null space is nullity. The nullity is a number. Okay, rank is a number, nullity is a number, null space is a vector subspace, row space is a vector subspace, column space is a vector subspace. Okay, so rank is the dimension of row space, dimension of column space, nullity dimension of null space. And what is a null space? Null space is set of solutions of equation AX is equal to 0. So there is a rank nullity theorem, very famous theorem, and usually this is also important through entrance point of view. Usually they ask you rank or nullity or some relation among that. So rank nullity theorem says you take any matrix, any M cross N matrix, the rank and the nullity, if you add, it will always be equal to number of columns, okay. So it will be equal to number of column of the matrix. So dimension of a matrix, here it will be, so, okay. So simply rank nullity theorem says rank of a matrix plus nullity of a matrix will always be equal to number of columns of the matrix. Further, there are properties, I think, so this is one example we have. So you can just check. So we have taken a matrix. It is 2 cross 3 matrix, and row is 1 2 0. Second row is 0 1 1. So you can check what will be the rank of this. So you can form a vector subspace, span of row vectors or span of column vectors. Then you find the how many of them are linearly independent, and that will be the rank. So there are two rows, you can check v1 v2, मान लो first row को v1 ले लो, second row को v2. So you take v1 as first row and v2 as second row. The c1 v1 plus c2 v2, put it 0, solve this equation, you will find c1 and c2 both are 0, and that's when both rows are independent, and then it will form a row space, and rank will be 2 because both row are independent. There are 3 columns. If you check, so they are not linearly independent. So if you take first column as u1, second column as u2, third column as u3, then c1 u1, c2 u2, and c3 u3, if you put 0, then all ci will not be 0 since columns are dependent. Only 2 out of them are independent. So that's why rank is 2. And rank plus nullity is number of columns. So if you find just rank, so nullity can be calculated using rank nullity theorem. Rank plus nullity is number of columns. So rank is 2, nullity is 3 minus 2. Okay. Okay, so now there are many properties. For example, like matrix is M cross N. So rank of the matrix A will be less than equal to M and less than equal to N both. Or you can say in one line, so rank of matrix A will be less than equal to minimum of M comma N. So there are many properties like this. So I will discuss some of you later. So next is row reduced echelon form. So when you say a matrix is in row echelon form or row reduced echelon form, or you may reduce any matrix into this form by applying a repetitive elementary operation. So if you apply repetitive elementary operation, so what is the definition? So what you have to achieve to convert a matrix into row reduced echelon form? So a matrix is in row reduced echelon form if and only if you have to ensure these conditions. The first is all zero rows are at the bottom. So all zero rows must be at the bottom. The leading entry, that is also called pivot, of each non-zero row is 1. So you have to make first non-zero entry, that is called leading entry. First non-zero entry of any row is the leading entry, and that is also called pivot. The pivot, leading entry, or first non-zero entry, they are same. So leading entry or pivot of each non-zero row is 1 and is to the right of the pivot above. So like if you go from top to bottom, so in the leftmost column you will find first, like for example, the row that comes first will have pivot in left side. The row that comes later will have pivot in right side. So stair type you can imagine. So 1, 1, 1 will be kind of stair types. Stairs like you are going down. So each pivot is the only non-zero entry in its column. The third condition is, so pivot below and above element of pivot element must be 0. So that is saying each pivot is only non-zero entry in its column. So what is use of this? So this is used to find rank. This is used to solve system of linear equation. And this is also used to find. So they are saying solving system of linear equation, it will be used. Finding rank, it will be used. Finding nullity, finding basis, and computing inverse of a matrix. So this can be used. Like if you remember in class 12th, you were finding inverse using elementary operation. So indirectly you were doing this only. If you go and open NCERT book matrix chapter, and there were two methods to find inverse. One is the formula 1 upon determinant A into adjoint A. The other was A into B is equal to I. Then you are applying repetitive elementary. Right one remains is the inverse or something like this. So there you were doing this indirectly actually. Now what is the trace of a matrix? So trace, so this is trace and determinant are defined only for the square matrices. So what is a square matrix? So a matrix with equal number of rows and columns. So like number of rows and number of columns are equal, then we call it a square matrix. So trace and determinant defined for only square matrices. Okay. So for a square matrix A, suppose order is n cross n. So trace will be sum of all diagonal entries. So what is the diagonal entry? So diagonal entry means AII, the element coming in the ith row and ith column. So like first row, first column element, second row, second column element, and all that. So sum of all diagonal entries will give you a trace of a matrix. Or other way, there is a theorem that if you find eigenvalues, then sum of all eigenvalues will also be equal to trace. Then there is a simply property, trace of A into B is equal to trace of B into A. So if you have a two matrix where multiplication is defined, then trace of AB and trace of BA will be equal. What is a determinant? So determinant is a number actually, a scalar matlab number. So a scalar DET is a small form, DET of A, that captures scaling factor of the linear transformation. And you know how to, it is actually determinant is a unique number associated with every matrix. And there is a proper way to find the determinant that you know. So it is defined via permutation, sum, or cofactor expansion. Then there is property determinant of A into B is equal to determinant A into determinant B, where A, B are square matrices of equal order. A is invertible if and only if determinant A must be non-zero. And determinant non-zero means A is called non-singular matrix. What is geometric meaning? So the area, volume, scaling. So if you have seen, we also find area of a triangle using determinant. In class 12, you might have seen. If you have a coordinates of a triangle, then you can find area using determinant. You have coordinates of a square, you may find area of that square using determinant. Now inverse of a matrix. So the definition of inverse is like a matrix B is said to be inverse of A if and only if A into B is equal to I. So here A into B is equal to I, you can say. So instead of A, here it is writing A inverse only. So matrix B is said to be inverse of matrix A if and only if A into B is equal to B into A is equal to identity matrix. So here they are saying A inverse exists if A is a square matrix, first condition, and determinant must be non-zero. They are telling the conditions, okay? And satisfying A into A inverse is I, or you can say A into B, B into A is I. And the formula is A inverse formula, you already know. This was from school days also. So 1 upon determinant A into adjoint A. Adjoint matrix, how you obtain adjoint matrix? You find minor and cofactor of each element of a matrix, and then instead of element, you put cofactors and then transpose. So these are all part of class 11, 12, school days book. You can go through matrix chapter from class 12th. Or there are other way, row reduction you can do, that I was telling. So AI to you can convert IA inverse. So this is all class 12 thing you can see. So what is the system of linear equation? So equation AX is equal to B is called system of linear equation, where A is M cross N matrix. X is actually column vector or column matrix with order N cross 1, and B is M cross 1 vectors. So if you define through matrix or determinant, so here I think they are considering A as square matrix. So here, so we are considering square matrix. So if A is a square matrix, then this will have unique solution if A is invertible. So this system will have unique solution even if and only if A inverse exists, or you can say A is invertible, or you can say determinant A is non-zero. And in that case, solution will be X is equal to A inverse B. So general solution using Gauss elimination, row reduced echelon form, we can calculate. So what is a homogeneous system? So when you put B is equal to 0, this becomes homogeneous system of equation. And homogeneous system always has one solution. That is a zero solution. That is also called trivial solution. So it will always have a trivial solution. X barabar 0. So there is no way you can have no solution in case of homogeneous system. So in homogeneous system, there is always a solution. So if you have more than one solution, means you have infinite solution. So in the homogeneous system, you have only two possibilities. Either only zero solution, or you have infinitely many solutions. There is no in between. Means only one solution or infinite solution. So only one solution means zero solution. Infinite solution means there are many other than zero. Okay, so non-trivial solution means non-zero solution. Exists if and only if determinant is zero in case of singular. So there are other way also to solve this system of equation. So augmented matrix. So you take a new matrix A and add one column as matrix B. So you can form augmented matrix A augmented B. Then if rank A and rank B is equal to number of columns of matrix A, then we this has unique solution. Rank of A and rank of A augmented B, they are equal, but they are less than n. N means number of columns. Then it has infinite solution. If rank of matrix A and rank of matrix A augmented B, they are different, then the system has no solution. So in general, a system has three possibilities. They have no solution, or unique solution, or infinite solution. The only three possibilities. There are no any fourth possibility. So based on rank, I think here actually our session 1 ends, but I will present something also. So here it is. So until this, we had session 1. Okay. So I will present some more. So this is what I have already taught in other batches. So here just I will repeat what we have done through PPT. I will repeat this. Okay. So we have seen what is a vector space. So that we have defined vector space is a set. Vector space is actually a set with two operation, addition, scalar multiplication, satisfying 8 axioms other than these two. So, and what is a subspace? So a subset of a vector space. Just I'm revising what we have done so far. It will take 5-10 minutes. Then I will give you a break for the next session. So a subset W of V is a subspace if and only if W plus dot. So plus dot is the operation, is also a vector space. And there were 3 conditions to check One is a zero vector must be in W. Second, you choose any two vector from W there. Sum must be in W. You find any scalar from field and any vector from W, then alpha into W must be in capital W. Okay, linear combination you have seen set of, so linear combination of vector v1, v2, vn is defined as c1, v1, c2, v2, and cn, vn. Okay, span was, so suppose S is a vector, S is a set of vectors v1, v2, vn. So span of S is the set of all linear combination. So means it's a set of c1, v1, c2, v2, and cn, vn, where ci are real number, vi belongs to set f. This is one example. There was also in PPT. It was 0, 1, and so actually here v1, v2 are dependent vector, you can see. So if you find their span, that will be C0 type. Similarly 1, 0, 0, 1, this was there. So if you find a span of v1, v2, they are linearly independent vector and span is R square. Then you have already seen a span is a subspace. Even it is the smallest subspace containing all vectors of set S. Then dependent, independent. So here I define dependent first. So you have vector v1, v2, vn. You say they are linearly dependent if there exists constant c1, c2, cn, of which at least one is non-zero. So out of this, at least one must be non-zero, such that linear combination is zero. So means you solve this linear combination. If you get at least one constant non-zero, then it is linearly dependent. And for independent, all constant has to be zero. So these are few examples you can check, like this 1, 0, 2, 0, they are dependent. Second example 1, 0, 0, 1, they are independent. You can check. Then second is set S is linearly independent, or vectors v1, v2, vn are linearly independent if and only if c1, v1, c2, v2, and cn, vn. So here is a typos. Cn, vn is 0 implies all ci must be 0. So you have to check a vector is Li or Ld. The only the thing is you just put linear combination 0 and check whether all Ci's are 0 or at least one is non-zero. So if all are 0, Li, at least one is non-zero, Ld. That is the way you can check. Like this example, 3 matrices I have taken, you can check their Li or Ld. So that I am solving C1, M1, C2, M2, C3, M3 is 0. Just you multiply these matrices, there will be one matrix. Then you put all 0, अब simplify करो, इसको solve करो. So 4 equations are there. If you solve, you got C1, C2, C3 all 0. Means these 3 matrices are linearly independent. Okay. Okay. So this you already know. So these 3 vectors are Li. If you put linear combination 0, all Ci will be 0. So this was doubt, I think. Then what is the basis? So a set S is basis of vector space if and only if span S should be V and S should be linearly independent set that you have seen. Here V1, V2 in R square vector space will form a basis, and dimension is number of element in the basis. Okay. So what is dimension of vector space? So V be a vector space, B is the basis of V, then number of element in the set B, that is basis, is defined to be dimension of vector space V. Okay. So like 1, 0, 0, 1, these two vectors form a basis and dimension is 2. So basis of vector space is not unique, but dimension is unique. Okay. So dimension of vector space will always be unique, but basis may not be unique. In fact, it's not unique. For any multiple you will take. So what is a row space? So it's a vector space generated by rows of a matrix. So like I've given this v1, v2, vm as rows. So vector space generated by rows of a matrix. Column space, vector space generated by columns of a matrix. So u1, u2, un are columns actually. So what is a row rank? Row rank is the dimension of row space. What is a column rank of a matrix? Dimension of column space. And they both are equal to rank of a matrix. So row rank, column rank, and rank will always be equal. So there are many different ways to find rank. So this I'm writing null space. So you have seen null space is a set of solutions of matrix equation Ax = 0. This null space, and dimension is called nullity. Rank plus nullity is number of columns. Okay. Then there are few elementary operations that you know, like elementary operations are these are 3 types. You can interchange any 2 row. You can change a row by Ri plus k time Rj, or you can change Ri as k time Ri. So you can change a row by multiplying some non-zero constant. So applying these three operations, you can convert a matrix into RREF, row reduced echelon form. So that was three conditions of row reduced echelon form. That same I have written in 4 points. That same thing. And any matrix can be reduced to RREF by applying multiple elementary operations. Trace sum of all diagonal entries. Determinant is a number associated with every square matrix, and you know the way how to find. Inverse, so a matrix A is said to be invertible if and only if AB is equal to BA is equal to I, and then B is inverse of A and A is inverse of B. So there are many ways to find inverse. So one of the ways is formula 1 upon determinant A joint A. If determinant is 0, matrix is not invertible and matrix inverse does not exist. Then you have a system of equation. So system of equation is AX is equal to B, where A is m cross n matrix, X is m cross 1 vector, and B is m cross 1 vector. So this will look like this. And then solution, so it has three possibility: unique solution, no solution, infinite solution. So they're a consistent system. So if it has either unique solution or infinite solution, so we call it consistent system. Inconsistent if it has no solution. So like here, consistent means at least one solution, inconsistent no solution. Then that theorem I was telling, if rank of A and rank of A augmented B both are equal to n, then system has unique solution. Rank of A and A augmented B are equal and they are less than n, then system has finite solution. If rank are different, then system has no solution. So this is also important point. How many solutions this system of equation has. So you have to apply this. This is, I think, easiest way I can say. Other way will be time taking. So this is important again. So they will ask you number of solutions of a system of equation. So you have to decide whether zero solution, I mean no solution, one solution, infinite solution. So this is the way you can check. Like one example I have taken here. Okay. So we have to check this system has how many solutions. Okay, so this is a system of equation. Then this is a matrix A. We have constructed A augmented B. So in the A, just you add one more column. Now we find rank of both A and A augmented B. So like rank of A, we calculated 3. Rank of A augmented B is 3. Both are equal and equal to number of column of matrix A. And that's why they have unique solution. If you solve, you will have unique solution. I think that's all. I will take 2 minute break and then we'll come again. Okay. So if you have any query so far, so I have discussed just session one part. Okay. So we have just discussed session one part. Okay. So if anyone has any doubt in that or queries in that, you may write in chat, or we'll take 2 minute break and then we'll continue. Okay. So take a break of 2 minutes and we'll be back in 2 minutes. Okay, I think we can continue. So you are asking, are most of the questions in exam expected to be numerical concept? Both will be there, and it's not just numerical and just. So conceptual and numerical both will be asked. Numerical will not be that much lengthy. It will not take too much time. Okay. When compared to CSR, is the statistics section use exam will be easier? It will be easier, obviously, compared to CSIR mathematical science. Okay. Okay, it will be easier than CSIR-NET exam. Okay, so let's continue. So this we have completed so far. Now we'll continue from this grams, Smith orthogonalization, then characteristic root, characteristic vector, characteristic polynomial, Cayley-Hamilton theorem. So they are easier part. It will take, I think, 10-15 minutes only. So this gram schematic orthogonalization process, actually what this says, if you have a linearly independent vector, then you can convert it into orthogonal as well as orthonormal vectors actually. So you can convert it orthonormal vector and also gonal vector, then further orthonormal vector actually. So goal is to, this is a process, or you can say this gives an algorithm to find orthonormal vectors corresponding to given linearly independent vectors, or orthogonal vectors corresponding to given. So there is independent vectors, then orthogonal, then orthonormal. There are three different terms. So given linearly independent vectors v1, v2, vk, so we need to produce orthogonal vectors v1, u1, u2, uk, and then later orthonormal vectors. So here vi's are independent, ui's are orthogonal, and ei's are orthonormal. Okay. So how will you achieve this goal? So goal is to compute or find, obtain orthogonal and orthonormal vectors corresponding to given linearly independent vectors. So you have linearly independent vector v1, v2, vk, and the orthogonal vectors are u1, u2, uk. So how will you obtain? So first u1 you take just v1 equal to v1. Then u2 you take v2 minus inner product or dot product of v2 with u1, and then u1 with u1 here u1. Okay. So u3 you'll take v3 minus, then you take inner product of v3 with u1 and upon u1 with u1, and then u1 here vector. This is inner product actually, dot product kind. A minus v3 u2. So you can understand a pattern. Like if I write u4, it will be v4 minus v4 u1 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 minus v4 u2 u2 u2, and then v4 v4 u3 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 like this. So inner product of u1 u1 this, and then further after obtaining u1 u2 un and uk, you can find e1. So e1 will be u1 upon norm of u1. So norm of u1 square will be inner product of u1 ui. So denominator, if you can see here, this is the u1 norm square. So later I think it will be there, or I will write. So so this is the orthonormal vectors. You just divide the vector ui by their norm or their magnitude. Okay. So how it is used? So it is used in QR decomposition. There are many decomposition in numerical analysis or linear algebra, advanced linear algebra. So that will be used here. The next is eigenvalue. So what is the eigenvalue and what is the eigenvector? So how to define? So characteristic root is the another name of eigenvalue. Characteristic vector is another name of eigenvector. Okay. So for a square matrix A, so a number lambda and a non-zero vector B. So that lambda is called eigenvector and V is called lambda is eigenvalue and V is the eigenvector. So a number lambda is called eigenvalue and number non-zero vector V is called eigenvector if and only if AV is equal to lambda V. So this is a definition you can say. AV is equal to lambda V is the definition corresponding. So where we say if AV is equal to lambda V, then we say lambda is eigenvalue of matrix A and V is the corresponding eigenvector. So lambda is eigenvalue, characteristic root, V is eigenvector. So you just have to solve this. And further you can simplify. So how to find eigenvalue? So to find eigenvalue, you solve this equation. The determinant of A minus lambda I is equal to 0. This is also called characteristic equation. So you solve this characteristic equation and the roots you will get are eigenvalues. So characteristic equation has roots, characteristic roots, and that is called eigenvalue. And eigenvector you can solve from. So first you have to find eigenvalue using this equation, and then you put it here and find V. So then you will get eigenvector is not unique. Okay. So corresponding to one eigenvalue, there are many eigenvectors. Okay. And the polynomial determinant A minus lambda I, this is called characteristic polynomial. So here we have defined eigenvalue, eigenvector, characteristic equation, characteristic polynomial. All are defined here. Which confusion? If you have any, you can ask. For example, you have this example like matrix is 2, 1, 1, 2. So 2 cross 2 matrix, you can just find this equation. So that will reduce to this. This is characteristic equation. Or left side is characteristic polynomial, you can say. Then you solve this. If you solve, lambda will be 3 and 1. So that is eigenvalues. Then what is the Cayley-Hamilton theorem? So Cayley-Hamilton theorem says every matrix satisfies its own characteristic equation. So here every square matrix satisfies its own characteristic equation. So if P lambda, determinant of A minus lambda I, that will be of this form, Cn lambda n and so on, C1 lambda C0. This is the characteristic polynomial you say. Then every matrix will satisfy this. If instead of lambda you put A, that will become 0. And this help us in finding A inverse, higher power, and then there are many applications in control theory, differential equation, all that. So this was, there is one example here, a matrix A is 1, 1, 0, 1. You find characteristic equation that will be lambda minus 1 square. And you can simply check A minus I, so that 1 in number will convert into identity matrix into matrix equation. Okay. So we are converting characteristic equation into matrix equation. So this polynomial, so lambda minus 1 whole square equal to 0 will convert into A minus I whole square equal to 0 in matrix equation. Okay. And further if you simplify, so you'll get this. So Cayley-Hamilton theorem says this will satisfy, and you can check that. This is a theorem actually. I think that was only unit 2 is very, like session 2 has only 4 content like Gram-Smith orthogonalization, eigenvalue, eigenvector, characteristic equation, characteristic polynomial, and then Cayley-Hamilton theorem. That is a very small part. So if I saw other PPT here, okay, so vector space, this was the one PPT. So this one I presented already, like a vector space is a set with, so just I will present this one also. So this is the class notes from my other lectures. So like I have defined already, vector space V with 2 operation which field F satisfy these 10 conditions. Okay. Okay, so these are few, I think, okay, that I was discussing there. So the first page was this, and then second page was this, I was presenting actually. So हमने यहाँ से start किया था ना. So the first part was here. Subspace है ना. Then there are some examples, questions है ना. ये सब कुछ questions हैं. Like first question was कि V is a vector space of set of all 2 cross 2 real matrices. W is a set of singular 2 cross 2 matrices. Now there are 4 options. So W is a subspace. There are 2 options. W is subspace or W is not subspace. So here you can check W will not be a subspace. Why? So if you take like this, see first example. So what I'm saying, just unit session 1 and session 2 combinedly I'm presenting again. So here this is the first question you can see on screen. V is a vector space of set of all 2 cross 2 real matrix. and W we have taken a subset as a singular matrices, determinant 0 wala. So matrices that has 2 cross 2 matrices that will determinant 0. So we asked whether W is subspace of V or W is not subspace. So to be a subspace, there was 3 conditions. 0 vector should be there. It is there because 0 matrix has determinant 0. You choose any 2 singular matrix, their sum must be a singular matrix. Second condition. So like M1, M2, we have taken 2 singular matrix of 2 cross 2. But if you add them, their sum will not singular. So this W is not a subspace. So this type of questions you may expect in exam. Okay. So second question is V is R cube. So R cube is set of XYZ where XYZ are R. Then there are 4 options and we ask the student to check which of the following is R a subspace of V. So first is like x square plus y square 0. Second is x plus 2y plus 3z is 0. Third is xyz is 0. Fourth is x is 1. So if you check all 3 conditions of subspace, you will find option A and B are true, C and D are not a subspace. Check, and if anything you have, please ask. So let's come to the next part. 1 minute, I think. So this we presented this subspace. You know, there are 3 conditions. These are 3 conditions. 0 vector should be there, sum should be there, and then scalar multiplication should be there. These were 2 examples that I was talking. So these are a few questions you can just see, and later you can watch the video and you can solve. These are few homework you can try. I think that's all, and then next I will present next part. So the next part is this that I was talking. तो इसमें क्या है देखिए थोड़ा देखते हैं इसको. So here characteristic roots you already know, but I will just repeat. So A is an n cross n real matrix. A number lambda is called eigenvalue, and a non-zero vector V is called eigenvector if and only if AB is equal to lambda V. So this is the definition of eigenvalue and eigenvector. You can see. So V is eigenvalue corresponding to V is eigenvector corresponding to eigenvalue lambda. So AB is equal to lambda V. If you simplify, then later you will see how this equation comes. So from this definition only this equation came actually, and using system of linear equation rules. So then this is a characteristic equation. A minus lambda I determinant is 0. Then characteristic polynomial lambda I minus a determinant you can take, or you can take a minus lambda I, that will work. So to find eigenvalue, you have to solve this equation, and to find eigenvector, you have to so AB is equal to lambda V, this equation. What is the Cayley-Hamilton theorem? It says every square matrix satisfies its own characteristic equation. Okay. Then the next part, I think. Okay. So second session was actually very less. It has very less content. In session 2, I will come to the chat section. If you have any doubt, you please ask. Sir, how can you define eigenvalue in layman? Layman term. Layman term you are saying. So I think we are defining eigenvalue actually just actually we are going through mathematics part, so it's defined mathematically. So eigenvalue is just the solution of characteristic equation, and what characteristic equation is, so A minus lambda I determinant is 0. It is defined mathematically, so we can define mathematically only. Yeah. Yes, they may ask, since it is part of syllabus, so they may ask you Gram-Smith orthogonalization. They will ask you. So they will give you like 3 vectors, linearly independent vector, and they will ask you to convert it into linearly converted to orthogonal vector. So there will be 4 options, and you will have to check whether okay. So there are many questions. I can give you. Yes. Okay, so yes, it's not lengthy calculation, just for the Gram-Smith. If you have only 2 vectors, it's very easy to calculate. If you have 3, very easy to calculate. It's not too much time taking. So you have linearly independent vector, and you have to, based on linearly independent, you have to find uh, orthogonal vectors, orthonormal. So you will have options and you can check. Please give us some example of questions based on Cayley-Hamilton. So you might have seen like there is a matrix and they are asking you to find a ki power 50. So that type of question will be asked. For this, I think you can see IIT JEE mains advanced question paper matrix theory. Even in 11th, 12th class, we find this type of questions, what you are asking. Cayley-Hamilton theorem. So for example, there are 4 options and they ask you which of the following equation matrix A satisfy. So this type of questions will be solved using Cayley-Hamilton theorem. Okay, 1 minute. We'll come to orthogonal matrices later. It was the third session, na? I will come. Sir, once can you say symmetric score? Yes, I will come to that. See, I have just discussed session 1 and session 2. Session 3 will start now. So these topics we have discussed briefly, not in much detail. Briefly we have discussed. So in that part, if you have any confusion, you may ask. Third part I will start. Third session will start now. Orthogonal, yes. MCQ explanation is needed. Yes, I think MCQ you have to solve since we have to finish everything in this. So MCQ you solve and we can discuss doubts. Book for Unit 2. Unit 2 is the just Cram-Smith orthogonalization. You can find any book like very high standard book. If you go, it's a Hoffman and Kuhn's linear algebra. That is abstract book. Some easier level if you come, so you can see there is a SOM series. I think there are 3000 solved problem book that you can go through, or you may start with some problem book. I think this is a problem part. It's not more theoretical. Session 2 is just problem time. You just solve questions. So Gram-Smith converts linearly independent into orthogonal and orthonormal vectors. Characterization root eigenvalue you can find through characteristic equation. Eigenvector you can find through definition. Characteristic polynomial you can find just by definition. And Cayley-Hamilton theorem says every matrix satisfies this equation. So like there will be equation and option, they will ask you whether they satisfy or not. So that will be solved by Cayley-Hamilton theorem. So I think this part, Cayley-Hamilton theorem part, you can find IIT JEE kind book also. You can solve. Or some solved problem. A SOM series book, I think some there you can search online. Solve. There are 3000, 4000 solved problem in there in that book. So you can find it. Okay. Okay, I think let's continue now. So let's continue the third session. So third session is actually symmetric matrices, and this is part of actually you can see school level content. Symmetric matrix, symmetric you might have seen already in 11th, 12th class, but you have to study still. So question will be asked on that, and then advanced question will be asked. So symmetric matrices, skew symmetric, orthogonal matrices, their characteristic roots. So eigenvalues. So symmetric matrix, I think A transpose is equal to A. Skew symmetric, A transpose is minus A. Orthogonal, A into A transpose is identity matrix. And then characteristic roots. So symmetric matrix have all real eigenvalues. Skew symmetric will have eigenvalue either 0 or purely imaginary. Orthogonal matrices will have eigenvalue plus or minus 1. So that is a property. Then positive definite matrix. A symmetric matrix with all positive eigenvalues. Positive semi-definite, a symmetric matrix with all non-negative eigenvalues. Quadratic form, X transpose AX. This is also a small part. So let's discuss this. So this PPT actually one of my team member have made. I have not made. So okay, let's start from here. So what is the definition of symmetric matrix? A square matrix A is said to be symmetric if A transpose equal to A. What is transpose? So in transpose, we interchange rows and columns. When we take transpose, first row becomes first column, second row becomes second column, third row becomes third column, fourth row becomes fourth column, and so on. So if transpose becomes equal to original matrix, then it is symmetric. And eigenvalues are always real. Eigenvectors can be chosen orthonormal. Yes. So you can have orthonormal eigenvectors corresponding to symmetric matrix. So if you go through diagonalizable concept, and there it is used. So symmetric matrices, real symmetric matrices are orthogonally diagonalizable. So this type of terms are there, theorems are there. Skew symmetric matrix, if A transpose is equal to minus A, then it is skew symmetric. When you take transpose and it becomes negative of the original matrix, then eigenvalues are purely imaginary or zero. So eigenvalues are purely imaginary or zero. Then we call it skew symmetric. Skew definition is A transpose minus A, and the property is it will have always all eigenvalue either purely imaginary or zero. Orthogonal, A transpose into A is equal to I, or A is A into A transpose I, or you can say A inverse is A transpose. And the eigenvalues are plus minus 1 only. Preserves inner product. So mainly we had to discuss like eigenvalue conditions with definition. So what is definition and corresponding eigenvalues? So the thing you can remember is they may ask you in exam 4 options. So symmetric matrix will always have real eigenvalue, yes. Skew symmetric matrix have eigenvalue 0 or purely imaginary. Orthogonal matrix have eigenvalue plus minus 1, modulus 1 or plus minus 1. Or if it is complex, then modulus will be 1. So I'm just talking about real symmetric, real skew symmetric, real orthogonal. Because in complex, the name changes. Symmetric becomes Hermitian, skew symmetric becomes skew Hermitian, orthogonal becomes unitary. So see the example, I think symmetry is 2, 1. So if first row and first column are same, you can say second row, second column same. Skew symmetric, 0, A minus, I think orthogonal was cos theta, sin theta, and there I think they cut the part. So what is a positive definite matrix? Positive definite, what is definition of positive definite, and what is definition of positive semi-definite? So a matrix A is positive definite if and only if X transpose AX is positive for all non-zero X, and it is positive semi-definite if and only if X transpose AX is more than equal to 0 for all X. So what are equivalent conditions? So a positive, a symmetric matrix with all eigenvalue positive are, so a real symmetric matrix is said to be positive definite if and only if they have all positive eigenvalue. And a real symmetric matrix is said to be positive semi-definite if and only if they have all eigenvalues non-negative. All leading principal minors will be positive, like 1 cross 1 principal minor you take, 2 cross 2, 3 cross 3, that will be positive in case of positive definite matrix. And A can be written as B transpose B sum matrix B. So I think this is not. So see here, A is a matrix 2, 1, 1, 2. This is a positive definite matrix. How you can check? So you see 1 cross 1 principal minor 2 and 2 cross 2 4 minus 1 3. So 1 cross 1 principal minor hai na, value is 2, and the 2 cross 2 itself determinant is 4 minus 1, that is 3. And it is symmetric matrix. So real symmetric matrix with all positive eigenvalue will be positive definite. So this is a positive definite. What is a quadratic form? So a quadratic form in variable x1, x2, xn is a homogeneous polynomial of degree 2. So it is defined like this, x transpose ax. And this was also in the definition of positive definite and positive semi-definite. यही quadratic form के help से हमने define किया था positive definite and positive semi-definite. Okay. So we have defined positive definite and semi-definite with help of quadratic form. And quadratic form is this, x transpose ax. If you open it, it will be summation aij xi xj, where ij you can take all possible values corresponding to matrix. Okay. So if A is n cross n matrix, then it will be A11 x1 x2 x1 square, A12 x1 x2 A13 x1 x3 and so on, A1n x1 xn and so on. So where A is a symmetric So A is a symmetric matrix. This is a definition of quadratic form. So you have already seen, we say QX is positive definite if QX is positive. So like A is positive definite matrix if QX is positive for all X non-zero. Positive semi-definite if QX is more than equal to 0 for all X belongs to Rn. It is indefinite, it takes both positive and negative, means it is neither positive definite nor semi-definite. So what is the connection? So the matrix A's definiteness determines the shape of the quadratic surface. So like if you make the graph in 3D, so it will give you the shape. So that so the book you want, so these are the references that have been used or content taken from. So those who are asking what are the references, you can see this. Okay, so references are this. Gilbert Strange, he was professor in MIT from last, I think, 60 years. अब रिटायर होगा ना, आई थिंक फ्यू इयर्स अगो रिटायर. लिनियर अलजेब्रा उनका बुक है दैट यू कैन सी. के हॉफमैन एंड कुंज, आई थिंक दे आर आल्सो इन एमआईटी. लिनियर अलजेब्रा का बुक है. दिस इज एब्स्ट्रैक्ट एंड वेरी हाई लेवल बुक. So some numerical questions you will find very less, and they are theoretical book. Then S. Exler, Linear Algebra Done Right. So these are books you can follow to cover this unit 2 linear algebra part. So I will present something more. So this we have already presented. This part I have already presented. Okay. Yeah, this we have presented. Just cut it. This I have already presented, and these are few questions that you can solve. So those who have access to some material, you can solve from there. So I will present this part. Okay. So I think this we have presented. Yes, eigenvalue, eigenvector. Yes, from here. And so this was Cayley-Hamilton theorem. Every square matrix satisfies its own characteristic equation. So if G lambda is the characteristic polynomial of matrix A, then GA is 0. Okay. So every matrix will satisfy its own characteristic equation. Transpose, what is transpose? If A is M cross N matrix, then A transpose will be AJI N cross M. So order will be reversed and the elements in ijth position will be changed into jith position. So what is symmetric matrix? A square matrix A is symmetric if and only if A transpose is A, like this. 1, 2, 3. So you can see first row, first column are same. Second row, second column are same elements. Third row and third columns are same elements. So when you take transpose, means if you interchange rows and columns, it will give you the same matrix. And that's why it is symmetric matrix. Skew symmetric, a square matrix said to be skew symmetric if A transpose is minus A or A is minus A transpose, like this. So there is a property that skew symmetric matrix will have 0 on diagonals always. Okay. And odd order skew symmetric matrix will always have determinant 0 because it will always have 0 as an eigenvalue. Odd order skew symmetric real matrix will always have 0 as an eigenvalue, and that's why it will have determinant 0 because determinant is product of eigenvalues. Trace is sum of eigenvalues. What is orthogonal matrix? A square matrix A is said to be orthogonal if A into A transpose is equal to A transpose in A equal to I. That is A transpose is A inverse. The properties, every real symmetric matrix has a real eigenvalue. Every real skew symmetric matrix has eigenvalue either 0 or purely imaginary complex number. So like this is A matrix, you can see this is symmetric. So we are calculating eigenvalue and we got 2 plus minus root 5. They are real numbers. B, you can see this is skew symmetric. You find the eigenvalue and you will get lambda as plus minus iota. So matrix P is skew symmetric and they have eigenvalue plus minus iota. They are purely imaginary. C, you can see this is skew symmetric matrix and you find the eigenvalue. So it will be something like 0 comma plus minus iota B. What is that B? You need to find. So 0 is always an eigenvalue in the skew symmetric matrix of odd order. Eigenvalue of orthogonal matrices are plus 1 or minus 1. So identity matrix is the easiest example of orthogonal matrix. So identity matrix is one of the orthogonal matrices. That is example of one orthogonal matrix. So it has eigenvalue 1, 1, 1. This is also another example of orthogonal matrix. It has eigenvalue 1, minus 1, 1. Okay. Then the people ask what is meaning of orthogonal vectors. Orthogonal matrix are different, orthogonal vector are different. In orthogonal matrix, its columns are orthonormal vectors. In orthogonal matrix, columns are orthonormal vectors. Rows are orthonormal vectors. So what is that ortho? So vectors and matrices are different, okay? So what I'm talking, here I'm just explaining what is the orthogonal vectors. So like V1, V2, Vn said to be orthogonal. So if you take dot product of any two or you take inner product, instead of you can also take inner product. So if you take inner product of like this, you can take Vi, Vj. So you write that way or you write, so you write this way or you write this way. So that so I mean dot product or inner product they are same. So I'm discussing inner product actually. The dot product means inner product. Inner product will be 0 for all I different than j. If you take inner product of same vector vi, that will be magnitude vi square or a norm vi square. What is the orthonormal? So orthonormal has one additional property, and that is norm should be equal to 1. So orthonormal means orthogonal as well as magnitude 1. Okay. So Vi, Vj will be 0 for I different than j. Vi dot Vi will be 1. Means mod Vi or norm Vi will be 1. Okay. Positive definite, you have already seen. A is said to be positive definite if X transpose AX is positive for all X non-zero. Semi-definite, matrix A is positive semi-definite if and only if X transpose AX is more than equal to 0 for all X belongs to Rn. So a real symmetric matrix is positive definite if and only if all eigenvalues are positive. Real symmetric matrix is positive semi-definite if and only if all eigenvalues are non-negative. Gram-Smith, I think that we have discussed. So here is again, you can see. So I will give example, I think here also. So we have given S1 is a set of linearly independent vector. S2 is the set of corresponding orthogonal vectors. And S3 is the set of corresponding orthonormal vectors. So how to obtain? And the good thing is they will all span to the same set, same vector space. So span of S1, span of S2, span of S3, they all will be equal to the common vector space. So S1 is V1, V2, Vn, given set of Li vectors. So how will you obtain orthogonal vectors? So that we have already seen. U1 you take just V1, U2 you take V2, then dot product or inner product of V2 with U1 upon U1 with U1, then take U1 vector there. And U3 similarly, V3 minus V3 U1, U1, U1 inner product U1, then V3 U2 inner product, U2, U2 inner product, and then U2. And U4 you can take V4 minus V4 U1, 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 and then V4 U2, U2, U2 in this. And similarly, you can go as many as one. In general, UN is Vn minus summation Vn Ui inner product, Ui Ui inner product, Ui. This Ui Ui inner product is norm Ui square actually. So like you have now set of orthogonal vectors. And now you divide this by their corresponding magnitude or norm. So you will have orthonormal vectors. So Wi is Ui upon norm Ui. Norm is nothing but this Ui dot Ui is norm Ui square. So take root. Okay. I think example I have not taken. Okay. So you can see example in book. If you have doubt, we can discuss. I think let's come to the chat part. Yeah, SOM series partner. So what is the book name you said about? Yeah, SOM, just Google it, SOM series. It will give you correct name. I'm just maybe pronunciating wrong, but you just write SOM series linear algebra. Google it. Problem book. It is a problem book mainly actually. SOM series linear algebra problem book. It has a lot of solved problems. So that you may go through. Sir, along with the PPTs, please share us the handwritten notes. It will be yes. I think I have given them. I don't know whether they uploaded or not. So I will merge it and give it to them. So along with PPT, I think I have provided them PPTs and handwritten notes also this part. So that is done. We come to, let's come to few problem section. So this problem is just AI generated. So just for the introduction purpose. So like for example, they are asking a vector space over R must satisfy closure under. So just their introductory level questions. Okay, so let's discuss. So vector space over R must satisfy closure property under what? So you can answer in chat. Okay, options. So whatever you feel, Hannah, you can answer. First question, what do you think? Addition, scalar multiplication, addition only, multiplication only, scalar multiplication only. It's a basic question on definition of a vector space. Okay, and it's easy now. So just you go through it. Then next is, which of the following is a subspace of R cube? So option A is correct. You all are telling right. Option A is correct. Then question number 2. Which of the following is a subspace of R cube? So A, B, C, D. In question 2, what do you find? Which of the following is a subspace of R cube? So vector space is R cube. So you tell the option in second question. Okay. I can take here the first one. A is okay. So this will result in x is equal to 0 and y is equal to 0. And this will result you x is equal to 0 and y is equal to 0. And that will be 0, 0. So that is also a subspace actually. And x, y, z, 0 vector is there. Yes. Sum will be there. Yes. I think it is also there. X is 1. So this will not be x, y, z is z. Z means integers. Integers. So E is a subspace पूछा है ना, है ना. तो इसमें थोड़े गलतियां होंगी. So you can just use your own mind, है ना, to tell whether, क्योंकि options may give you just one option, but you can just use your own mind. है ना. Just for the introduction purpose, I have just made using AI. So these questions are made by AI actually. So we are saying x, y, z all are integers. So 0 vector is there, yes. And then sum of 2, if you take, they are integers, sum will be integer, yes. Scalar multiplication integer, no. This will fail, you know why? Because if you take alpha as 1 by 2, so 1 by 2 into integer will not be integer. So I think A and B is fine. So आप लोग A, B answer कर रहे हैं? Yes, A, B, हाँ. So what is answer for 3? The set x0, where x is real number, is a subspace of R cube because, अब आंसर आपसे पूछ रहा है कि ये subspace है, they are given. Why do you think it is a subspace? So it contains 0 and it's closed under addition, scalar multiplication. So subspace के लिए 3 condition था. It is, so just they are just asking whether you know the theorem or not. So that theorem was there. Only one vector, both A and C. It is a line through origin. It is a line through origin. Y is 0. Y is 0. The x-axis है ना. ये x0 मतलब all points on x-axis है ना. So it's a set of all points on x-axis. तो 0, 0 है. You take sum of any two, it will there. You take constant, it will be there. तो बस I think पहला ही okay है. क्या होगा? 3 में आप लोग A D कर रहे हैं. D में क्या है? D तो पढ़ाई में ध्यान दिया. So what is D option? Both A and C. अब यूज कर सकते. It contain only one vector. Okay. तो वैसे तो आप तो यहाँ पे क्या ना, ये ऑप्शन ऐसे बना दिया है, बट एग्जाम में ऐसा ऑप्शन नहीं रहेगा कि A भी सही, B भी सही, ऐसा रहेगा फिर A and C. तो एग्जाम विल नॉट आस्क यू दिस टाइप ऑफ क्वेश्चंस, है ना, कि A and C. मतलब दिस टाइप ऑफ ऑप्शन एग्जाम विल नॉट हैव both A and C. It will have one option, then only one option will be correct. So this is also true, only one vector, but being only one vector is not sufficient to be a vector space, right? If it has only one vector, if I give you some vector space that has only one vector, does it guarantee to be a vector space? If I write 1, 2, for example, so can you say this is a vector subspace? So being a single vector doesn't guarantee it is a vector vector subspace, है ना? It is, है ना? So it doesn't mean, or this is not only one vector. It contains only one vector. Do you think? There are many, na? 1, 0, 2, 0, 3, 0. Only A will be correct. Huh? Okay. So being one vector doesn't mean it is a vector subspace. Let's come to fourth. So they are just, you can say, I'm just collecting those points we have discussed so far. They are not very difficult questions. They are just definition based question what we have seen through slides. So that I'm just asking whether you can recall or not. So these are very question based on that only. You remember or not? The span of vector this is set of all linear combination, the set of all linearly independent combination, the set of vector orthogonal to them, the null space of the matrix with these vectors as row. So I think a simple definition here. Fourth, okay? Yes. Fifth, the set of vectors v1, v2, vk linearly independent if. So what do you think? Why it is linearly independent? The only solution of this is this. The only one vector can be written as the combination of the others. Their span the whole space and they are pairwise orthogonal. तो अगेन ये सब में ए ही लग रहा है ना? ये ना इंडिपेंडेंट की बात कर रहा है ना, एल की बात कर रहा है. सो ओके. Yes, I think it's fine. So next, let's come to 6. They're asking in R3 the maximum number of Li vectors are is कितने linearly independent vector R3 में हो सकते हैं? R3 एक set of all points हैं x y z. R3 set में infinite vectors हैं, और R3 में कितने Li हो सकते हैं एक साथ? So maximum number of linearly independent vector आपसे पूछ रहा है कितने हो सकते हैं? 6th. तो 3 ही हो सकता ना यहाँ भी, ज्यादा तो नहीं हो सकता. मैक्सिमम 3 ही हो सकता है. यस. नेक्स्ट 7th है अ बेसिस ऑफ अ वेक्टर स्पेस V इज. अगेन डेफिनेशन दे आर आस्किंग वेदर यू रिमेंबर डेफिनेशन और नॉट. सो बेसिस का डेफिनेशन क्या था? A set that span linear independent and minimal spanning set equivalent to maximum spanning set. तो सब में ए ऑप्शन ही पहले सही लिखा है क्या इसने? है ना? तो ये एआई जो क्वेश्चन बना रहा है उसमें पहला ऑप्शन जो है वो ए ही रख रहा है. अब है 8th क्वेश्चन डायमेंशन ऑफ आर एन. तो इससे कुछ नहीं, आर एन का डायमेंशन है ना, इसमें एन वेक्टर होगा, तो ट्रिवियल है. 9th ये इफ डायमेंशन ऑफ वी इज एन एनी सेट ऑफ एन एल आई वैक्टर इन वी इज. सो व्हाट डू यू थिंक? बताइए. 9th का बताओ. 8th तो ऐसे ही आर एन में एन डायमेंशन था, तो 8th ओके है. सो व्हाट इज द आंसर इन 9th? अगर किसी वेक्टर स्पेस का डायमेंशन n है तो एनी सेट ऑफ n li वेक्टर्स क्या होगा? बेसिस होगा, नॉट नेसेसरी बेसिस होगा, li ld होगा, स्पैनिंग होगा बट नॉट नेसेसरी इंडिपेंडेंट होगा. व्हाट डू यू थिंक? तो सबसे वैसी बेसिक प्रॉपर्टी है, अगर डायमेंशन n है ना तो आपको पता है कि डायमेंशन n है, तो n सेट वाला अगर li वेक्टर ले लोगे ना तो वो बेसिस बनाएगा ही, मतलब स्पैनिंग ऑटोमेटिकली हो जाएगा. इवन इफ यू हैव अ सेट विथ n एलिमेंट हैविंग स्पैनिंग प्रॉपर्टी तो ऑटोमेटिकली li हो जाएगा, तो वो बेसिस हो जाएगा. ठीक है. 10th क्वेश्चन देखिए. द सबस्पेस दिस हैज डायमेंशन. इस सबस्पेस का डायमेंशन क्या होगा बताइए. सो व्हाट इज डायमेंशन ऑफ दिस सबस्पेस? 10th क्वेश्चन का आंसर बताइए. चेक कीजिए 10th का क्या होगा. तो 10th में सम वन आंसरिंग ए सम बी, व्हाट इज एक्चुअल आंसर। तो देखो डायमेंशन होगा नंबर ऑफ फ्री वेरिएबल, आप ऐसा समझो कितने फ्री वेरिएबल है इसमें। तो जैसे यहाँ पे x इज इक्वल टू वाई आ जाएगा एंड z तो जीरो हो गया, z तो फिक्स हो गया। तो अगर मैं इसको रीराइट करूं तो ये ऐसा होगा x x जीरो, ये सेट इसमें रिड्यूस हो गया, ठीक है, ऐसा है। तो इसमें कितने फ्री वेरिएबल दिख रहा है, एक, just one free variable, the dimension is 1. So just one free variable. How many free variables are there? So free variable is just one, x only. If you know the x, other variable already determined है, x अगर 1 है तो y भी 1 होगा, z 0 हो जाएगा, है ना। और I can elaborate more, I can write is span of vector 1 1 0। सो इसके बेसिस में ना सिर्फ एक वेक्टर आएगा, और ये एल आई भी है, सिंगल नॉन जीरो वेक्टर हमेशा एल आई होता है, तो ये वेक्टर एल आई भी है तो ये बेसिस बना लेगा, ठीक है। डन ना, क्लियर है 10 का। ओके, नेक्स्ट देखिए 11 देखिए। अब ये फॉर्मूला है जो कि अभी डिस्कस करना था, मुझे किया नहीं है। सम ऑफ टू सबस्पेस इज अ सबस्पेस, वो हमेशा थ्योरम है ये। इंटरसेक्शन ऑफ टू सबस्पेस इज अ सबस्पेस, दिस इज अ थ्योरम। यूनियन ऑफ टू सबस्पेस मे नॉट बी ए सबस्पेस, ठीक है। तो क्वेश्चन ये है फॉर्मूला क्या है इनमें से, आपको फॉर्मूला याद है? ये फॉर्मूला है ना, ये फॉर्मूला है सिंपल। हाँ, एडी क्या बता रहे हैं, अलग अलग सबका आंसर है। नहीं ये नहीं होगा, ये पहला फॉर्मूला है, डायमेंशन ऑफ यू प्लस डब्ल्यू इज डायमेंशन यू प्लस माइनस इंटरसेक्शन, ठीक है। क्योंकि यूनियन का फॉर्मूला जैसे होता है ना सेट में, या आपने प्रोबेबिलिटी में पढ़ा होगा, प्रोबेबिलिटी ऑफ ए यूनियन बी, इट्स लाइक दिस वन, बट यूनियन ऑफ टू सबस्पेस विल नॉट बी अ सबस्पेस इन जनरल। तो यहाँ सम होगा हमेशा सबस्पेस, सम के लिए फॉर्मूला होता है। द इंटरसेक्शन ऑफ टू सबस्पेस इज ऑलवेज अ सबस्पेस, तो ये थ्योरम है, ठीक है। इंटरसेक्शन हमेशा सबस्पेस होगा। V is a vector space of dimension n, U is a subspace of dimension k, then any basis of U can be extended to a basis of V by adding। चेक कीजिए, तो क्या लगता है 13 का आंसर बताइए। क्या लगा, क्या होगा इसका आंसर? वी वेक्टर स्पेस डायमेंशन है ना, एन है, यू है के का, तो कह रहा है कि बेसिस ऑफ यू कैन बी एक्सटेंड, एक्सटेंड तो कर सकते हैं टू द बेसिस ऑफ वी। तो कितने वेक्टर ऐड करने होंगे हमें? तो के यहाँ छोटा, ये कहना ये चाह रहा है कि के इज लेस देन एन, ठीक है, के इज लेस देन एन है, तो हमें एन माइनस के ऐड करना पड़ेगा, है ना। तो एन माइनस के अब ऐड करेंगे, सो इफ यू ऐड दिस, ओके। 14th सेट ऑफ 2x2 रियल मैट्रिसेस इज अ वेक्टर स्पेस ऑफ डायमेंशन, इसका डायमेंशन कितना है? ये 14th क्वेश्चन का आंसर क्या होगा? बताओ भाई। तो 14th का आंसर आपका कितना आया? सी आ गया ना। सेट ऑफ 2x2 रियल मैट्रिसेस, सेट ऑफ 2x2 रियल मैट्रिसेस वेक्टर्स, तो 2x2 में कितने एलिमेंट होते हैं? ए बी सी डी, चार एलिमेंट है, तो चार अननोन है, चार फ्री वेरिएबल है। सेट ऑफ 2x2 मैट्रिक्स है ना, कुछ कंडीशन दिया है, कुछ कंडीशन तो दिया नहीं है, तो वेरिएबल रिड्यूस कैसे होगा? चार, जितना नंबर ऑफ फ्री वेरिएबल ये समझ लो, या नंबर ऑफ अननोन वेरिएबल समझ लो, कितने अननोन? चार है, तो मुझे इसको डिटर्मिन करने के लिए ए बी सी डी चार हो, या स्पैन लिखोगे ना, तो ए बी सी डी चार फ्री वेरिएबल, चार आंसर होगा। तो आप लोग आंसर मतलब कैसे आ रहा है 14 का? ये सब लोग सी आंसर बता रहे हैं, क्यों भाई? सी में क्या है? टू क्यों होगा? 2x2 में कितने एलिमेंट होते हैं? चार एलिमेंट होते हैं ना, तो डायमेंशन 4 होगा। नंबर ऑफ फ्री वेरिएबल, तो आपको 2x2 मैट्रिक्स डिसाइड करना है, तो यूनिट फोर फ्री वेरिएबल, देयर आर 4 वेरिएबल्स, तो यहाँ स्पैन करोगे तो स्पैन में चार वेक्टर आएगा, 1 0 0 0 0 1 0 0 0 0 1 0 1 0 0 0 1, चार आएगा, ठीक है। Which of the following is not a subspace of the space of all real function? 15 बताइए क्या होगा? कौन सा सबस्पेस नहीं है? है ना, ये स्पेस ऑफ रियल फंक्शन ये है, और किस कौन सा सबस्पेस नहीं होगा ये बताना है। सो 15 का आंसर बताइए। तो जीरो फंक्शन होना चाहिए, बस जीरो फंक्शन मस्ट बी देयर। सी में है F0 1 है, तो F0 अगर 1 है तो जीरो फंक्शन शुड बी देयर ना, पहला जीरो फंक्शन होना चाहिए, एफ एक्स बराबर जीरो होना चाहिए, तो एफ एक्स बराबर जीरो, ये F0 1 है, ऑल फंक्शन विथ F0 1, F00 मतलब क्या हुआ? ओरिजिन से पास कर रही है। द फॉलोइंग इज नॉट अ सबस्पेस ऑफ द स्पेस ऑफ ऑल रियल फंक्शन, तो कॉन्टिन्यूस जीरो फंक्शन है, सम ऑफ टू कॉन्टिन्यूस होगा, एंड डिफरेंशिएबल में भी ओके है, तो ये दोनों तो है, बस सी और डी में से कोई नहीं होगा, तो कौन सा नहीं होगा? F00 है, इसका मतलब है तो जीरो वेक्टर मस्ट बी देयर, तो ऑल फंक्शंस विथ F0 इज 1, तो F01 हो गया, ओके, तो जीरो कभी होगा किसी पॉइंट पे, जीरो फंक्शन इसमें एफ एक्स बराबर जीरो कब होगा? अच्छा, एफ जीरो जीरो मतलब ये ए एक्स टाइप का होगा ना, एफ एक्स बराबर टू एक्स थ्री एक्स ऐसा। एफ जीरो वन हो गया तो ये होगा टू एक्स प्लस वन जैसा, तो ये तो कभी बन नहीं पाएगा। ठीक है, सी इज नॉट अ सबस्पेस। A row space of a matrix A is a span of its row vectors. Easy definition. Column space of matrix A is a subspace of column vector. Column कितने होते हैं? तो m क्रॉस n है ना, कॉलम n है, तो n होगा तो आर एन का होगा, b का, है ना। Rank of the matrix is equal to dimension of row space, dimension of column space, number of independent rows, all of the above। इनमें चारों ऑप्शन है सही है, लेकिन डी बोला है तो all of the above में आ जाएगा, एक चुनना है तो। For m cross n matrix the nullity is equal to, तो number of column minus rank, ठीक है। रैंक nullity theorem says rank plus nullity is number of columns, ठीक है। A matrix in row reduced echelon form has a following property: each leading entry is one and the non-zero entry in its column, ठीक है, पहला ही लगता हो जाएगा, ठीक है। रैंक ऑफ अ मैट्रिक्स कैन बी फाउंड बाय काउंटिंग द नंबर ऑफ नॉन जीरो रोज इन द आरआरडीएफ, ये थ्योरम है, काउंटिंग ऑल रोज काउंटिंग, ठीक है। ए इज एम क्रॉस एन मैट्रिक्स विथ एम लेस देन एन, देन नलिटी इज एट लिस्ट, तो रैंक तो होगा वो एम या एम से कम ही होगा, है ना। तो रैंक प्लस नलिटी यहाँ एन होना है, और रैंक हमेशा एम या एम से कम ही होगा, तो नलिटी एटलीस्ट वन तो होगा। अच्छा वन है, लेकिन यहाँ पे हमें इसको एम और एन में कंपेयर करना ना, तो एम क्रॉस एन की मैट्रिक्स है ना, तो रैंक तो जो भी छोटी है उससे भी छोटी होगी, तो एम से भी छोटी रैंक होगी, और रैंक प्लस नलिटी एन हो जाएगा, तो एन माइनस रैंक, और जो रैंक है दैट विल बी लेस देन इक्वल टू एम, ठीक है ना। रैंक जो मैट्रिक्स का है वो लेस देन इक्वल टू एम होगा, तो माइनस एम मोर देन इक्वल टू एन मोर देन इक्वल टू एन माइनस एम, यहाँ से एन माइनस एम होगा ना, ये हो जाएगा, ठीक है। 23 का 24, the row space and column space matrix have same dimension. Which of the following operation does not change the row space of a matrix? रो स्पेस को चेंज नहीं करता, एलिमेंट्री रो ऑपरेशन, ट्रांसपोजिशन एंड कॉलम ऑपरेशन, मल्टीप्लाइंग बाय अ स्केलर। कौन सा ऑपरेशन है जो डज नॉट चेंज द रो स्पेस ऑफ अ मैट्रिक्स, मतलब रो स्पेस जो पहले वही रो स्पेस रहेगा, ऐसे ठीक है, रो ऑपरेशन होगा, ठीक है भाई। सो आई थिंक दैट्स ऑल, मुझे यहीं पे इसको खत्म करता हूँ, ऐसे क्वेश्चंस कितने सारे हैं, बहुत सारे क्वेश्चन हैं, तो आप इसको सॉल्व करना, देन वी कैन हैव सम क्लासेस, 100 क्वेश्चंस हैं इसमें। आंसर की है ना, मे नॉट बी ट्रस्ट वर्दी, तो यू मे नॉट ट्रस्ट 100%, आप चेक कर सकते हो, बट अपना बुद्धि का ज्यादा इस्तेमाल करना, ठीक है। सो क्वाड्रेटिक फॉर्म, दिस इज स्ट्रिक्टली कॉन्वेक्स इफ एंड ओनली इफ कॉन्वेक्स, ठीक है। तो कॉन्वेक्स होने के लिए क्या होना चाहिए? पॉजिटिव डेफिनेट। तो इसे बस सॉल्व करो, है ना, ये प्रोवाइड कर देंगे वो लोग, एंड देन विल डिस्कस। तो बस डेफिनेशन बेस्ड एंड इंट्रोडक्शन बेस्ड क्वेश्चन है। चले तो आई थिंक मैं यहीं स्टॉप करता हूँ। सो इट्स 6 to 8 सेशन, 2 घंटे का हुआ है, एंड थैंक यू एवरीवन। कुछ है डिस्कस करने को तो पूछो, ठीक है। यू हैव एनीथिंग टू डिस्कस तो बता सकते हो, ठीक है ना। तो थैंक यू। अभी मेरा जो काम था, जो मुझे दिया गया था, तो वो हमने आपको डिस्कस किया है ना। सो वी हैव डिस्कस्ड दिस पार्ट, तो हमने इसमें जो भी दिया गया था, यूनिट 2 है ना, एनालिसिस मैट्रिक अलजेब्रा वाले पार्ट में हमें दिया गया था पार्ट 3 वाला, तो पार्ट 3 में था सेशन 1 2 3 में ये था, तो सेशन 2 बहुत छोटा सा था, सेशन 3 भी छोटा सा था ही था, है ना। तो इसमें हमने अराउंड 1 घंटे दिए हैं, और इसमें अराउंड आधा आधा घंटा, मतलब ऐसे 15-15-20 मिनट दिए हैं, तो हाफ बार दिए, तो 2 आवर्स हमने इसमें स्पेंड किए हैं, दैट्स वी हैव डन नाउ, है ना। आपको यही कहना है कि आप ज़्यादा से ज़्यादा क्वेश्चन सॉल्व करो एंड गेट कॉन्फिडेंस इन प्रॉब्लम सॉल्विंग, देन हो जाएगा। सो आई थिंक दिस इज माई डिटेल, एंड कैन मेल फॉर एनीथिंग, है ना, you have। यहाँ तक डिस्कस किया, ये यहाँ तक चले गए थे. तो दिस वाज द रेफरेंस, यू कैन, है ना, सी. सो दिस रेफरेंसेस यू मे फॉलो. एंड दिस इज माय डिटेल. थैंक यू. मिलते हैं नेक्स्ट क्लास में. आई थिंक दैट्स ऑल. Yeah. So, Vishal, you're right. Can you please share the PPT? I think I will share them. WhatsApp group. अच्छा, you tag me in the WhatsApp group. Okay, I will share. So I think मेरा नंबर और ये सब तो होगा ना, डिटेल ऑलरेडी. मैं मोबाइल नंबर यहाँ टैग कर देता हूँ. आप मुझे ग्रुप में टैग करो, मैं पोस्ट कर दूंगा, है ना. तो यू कैन जस्ट, है ना, ये देखो मैं जिस ग्रुप में हूँ, अगर आपके साथ अगर कोई कॉमन ग्रुप है तो आई विल सेंड दिस नोट्स. Yes, usual. Thank you. So thank you, है ना. For anything help you can contact. Thank you. Thank you. So free doubt session भी मैं चलाता हूँ. So if you have any doubt, you can join in, है ना. You can ask your doubts. तो डाउट सेशन फ्री रहता है, ठीक है ना. जैसे आपने यूट्यूब चैनल का जिक्र किया, तो हम लोग लाइव सेशन रखते हैं रात को 11 से 12. तो उसमें हम फ्री डाउट सेशन लेते हैं. तो यू मे ज्वाइन एंड आस्क फ्री. ठीक है. तो any question or any query you can discuss with me if I can help. मैं स्टॉप करता हूँ. I think Anil, should I stop now? Okay, thank you.